Hello.
Hi guys. Hello.
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 Hi there.
Hello.
Hello.
Hello. So, hello everyone, and welcome back to this week's tech session. Today, our speaker will be Perta, and he will be showing us functional programming 1 out of 3 series. And today we're going to do the basics of it with examples in C# and F#. Thank you so much for joining today, and thank you to Perta for presenting today. And yeah, Perta, you can take it away.
Thanks, Pramna. Let me just share my slides. What the hell? What the hell? Hang on. Right, here we go. People can see my slides. Yes, no, maybe. Okay, yes, okay.
Yeah.
So I've deliberately inserted some mistakes just to make sure that folks catch me and it remains interesting. But so yeah, certainly spot them. There are some very obvious mistakes. Maybe not. Oh yeah, the cat is right here. I've given her food she hasn't eaten, and now she's gonna eat my head. But anyway, we'll ignore it. Okay, so all right. So this is going to be from where Andre left off. He presented a taste of FP. Today I will dive down deep into elevator pitch, sales pitch, whatever you call it, so that I can fold my hands and beg you to start using it. We'll see if that works. Right, so this will be the very basics. There are 2 more talks pending in this series, so total 4 talks. First was Andre, the rest of the 3 talks I'll do. Right, so let's see. Again, right, so this is the foundational skills of software engineering. We've covered a few of these, right? Today we'll cover this. The whole idea is that if you have essentially mastered these, right, and this is like any other skill, so you just practice, learn from people who have done it before, and practice again, learn some bit of theory, practice again, and then you master it, right, over a period of 20, 30, 40 years. You can design any system on the planet, right? Any software running system in the planet, right? Also that the higher the level of mastery, the lesser is the stress at work. So you can now focus on interesting things like business problems or what gets customer the most value, right? As opposed to getting stressed out with why your code is not working when it was not supposed to be working in the first place. Right, and then we've already covered 1, 2, 3, 9. This is a weird numbering system, just humor me. This will be the 4th, this will be the 5th talk, number 4, FP 1 of 3, the very basics, right? All right, and okay, some warning, right? Usual stuff. This one definitely has a learning curve, right? So try them out in pet projects. Excellent way to build skills. Hit me up. I'm happy to pair program with you. You know, I love doing this stuff. This truly is awesome, right? And then ensure EM approval before trying it out at work. Otherwise, I'll have the crap beat out of me by your EMs. To be fair, I'm the only one wearing pants in that group, but it won't help when I'm getting beaten up. All right, so the usual stuff, right? Anybody knows who these people are?
Alan Turing in the middle.
Yeah, Turing in the middle.
Spot on.
Haskell Curry on the right, and Kurt Gödel on the left.
Gödel on the left is right. That's not Curry.
Isn't it von Neumann?
It's
Nope.
Alonzo Church, actually.
It's Alonzo Church. Okay, so these are our forefathers. And when I mean forefathers, I literally mean forefathers of our profession. These are the guys in 1930s. They published seminal papers. So Alan Turing comes up with this Turing machine, which is basically models what a computer can effectively compute. And those days, computers were humans, basically, you know, going through steps and computing any equation. So when you refer to a computer in 1930s, think of it as a human, right? So Alan Turing comes up with his Turing machine, which is the ultimate model for what can be computed, what cannot be computed, you know, halting problem and so on and so forth. Then Church was an advisor. Church comes and says, reportedly comes and tells him that is all bullshit. That's not the way to do it. So he comes up with something called lambda calculus. He says, okay, this is the way to build something that is proofs when something is or something isn't effectively computable. Then Gödel, of course, right, is genius. By the way, he was born in Brno. So Gödel comes and says, you guys are both wrong. The way to do it is through recursive functions. And then, of course, he goes and publishes, you know, just fascinating, the history here. Eventually, all 3 of them prove that they're all saying the same thing. So Gödel's primitive recursion, Church's Turing's Turing machine, and Church's lambda calculus, they're essentially the identical things seen from 3 different ways. Now, there's a reason why I got this in, right? So typically when folks start learning functional programming, right, and this is from what I've seen and what my experience was, you'll often hear statements like, how do I write a for loop in functional programming? That just beats the point, right? So that's not even a wrong question in functional programming, right? So now what often happens is that we try to apply our structured thinking to build functional code, right? And hopefully through this talk, I should be able to break that, saying that you need a fresh beginning, you know, you need a fresh start. In the end, of course, they're all the same thing. That's what these 3 guys did to prove that lambda calculus equals Turing machine in expressive power, and Turing machine equals primitive recursive functions in expressive power. So they're technically the same thing, but nonetheless, it requires a bit of different mindset to start. That mindset is the one that builds your skill as a programmer, right? It's not a theoretical mindset. This is the one that helps you write top quality code, right? Code that is resilient, code that is future proof. Remember, I said code, not design, right? So we don't do future-proof designs, we write future-proof code. There's a difference, right? All right, so also, right, again, like I said, FP can do anything that O and structured can do, and vice versa. That is what church theory hypothesis or thesis is. Both shape your thinking, right? So you need both. You need to be good at both. However, some constructs are more elegant in one versus the other. You'll need both to be a really kick-ass engineer, right? And it's highly recommended to be able to mix and match depending on the problem, right? And here are 13 ways to, just 13 starter ways to mix and match the two. Stay out of stupid online debates. You know, FP is better than OO, Haskell is Jesus' second coming, and you know, shit like that. So just stay out of that nonsense. It's a waste of time. It literally is a waste of time, because that's what church and theory have proven, right? It's a waste of time. Stop me if you guys have any questions. Otherwise, I'll go.
Actually, second point there with Haskell is right.
There you go. See, we've got already somebody here. Okay. All right, man. Okay. We'll talk offline in the car parking. Yeah. Okay, agenda. Right? So this is going to be the elevator pitch, the sales pitch. It'll take more than 2 minutes. The awkward squad. Real code handling the awkward squad. It'll be a you know, fairly short code, but something real world. This is where I'm planning to break. If people are going to ask how to write a for loop in functional programming, hopefully after this section 3, you will not be asking that question, right? So how do you write for loop in functional code? That's not even a wrong question in functional programming, right? So you need to change your thinking if that's how you're thinking. Slight detour about functions or maths and functions in functional programming are basically the same thing, right? And then how do you go about mastering this, right? So it's very limited. You know? So the challenge is not all that big, right? It's much simpler than structured and all, right? These are some of the things we'll quickly cover. There's a lot of material, so I'll just never mind, right? So even if you break it in the middle, we can always come back in the next session and then resume. I think I got the agenda messed up, but nonetheless, right? That's pretty much it. Okay, if you guys don't have questions, I will dive right in. All right, awkward squad, right? We cannot write cute code most of the times because of these guys, and these are this is also the reason why you get paid so much, right? If it weren't for this, then you would be pushing paper. Your job would be as good as pushing paper somewhere else, right? What is that? So let's just see what an awkward squad is, right? So basically, people who resist change or obstruct change through either incompetence or by deliberate association, right? And that is very much applicable to the awkward squad when in reference to programming, right? Simon PJ is our guy. He's one of the founders of Haskell and one of the key contributors of Haskell, the programming language. He's in Cambridge. Say hi to him over Teams. Basically, he says that you not only need to write beautiful but also useful code, right? And to write useful code, you have to deal with these following 4 members of the awkward squad, right? And they are basically, if not for the external world, your code will be very beautiful, albeit useless. So what are the 4 things? Input and output, right? So how do you meaningfully receive stuff from outside world and send stuff to outside world, right? Again, this is about, you know, the outside world is very erratic, doesn't behave in the way that we want to. Error detection and recovery, things don't work the way I expect them to. Exceptions, H results, timeouts, and all crazy stuff. Concurrency and parallelism, especially since Moore's law isn't our friend anymore, right? Started sucking sometime in the last decade. And interfacing to external libraries, right? You don't write all components yourself. You tend to reuse your partner code or you know, open sources and things like that. So this fits right in with what the definition of Wikipedia is, right? These are essentially the aspects that resist or obstruct change in your code, right? And if you can't change your code, which means you can't meet your business requirements, which means you can't, your team is not useful to the business, right? Which means that you will have to eventually you will have to find a way to handle this, right, elegantly, in a future-proof way. to be able to make your code amenable to change, so that when the PM says, hey, can we get this done, your question is, okay, how much, not okay, no, and that kind of stuff. Anybody can connect to this or any questions, let me know. Right, so this is essentially the awkward squad. Let me get straight down to handling the awkward squad, right? So the main thing, right, the main elevator pitch for functional programming is that it makes this bad shit look good, right? And not just look good, but in essence, you learn about 7 patterns, and using the 7 patterns, you handle all combinations of the awkward squad, right? It's just those 7 patterns. Right? It's a very consistent language, consistent way of reasoning, consistent way of programming, right? And when I say reason, right, reason isn't logically reasoning. If this does this, then and that does that, then this and this should be doing this, right? You can reason like that. You can't do the same with structured or O, because you never know what the structure program underneath is doing, right? It can be doing a lot of bad shit underneath. You have no idea. Okay, so let me dive right in. So this is some bit of code that I wrote about, I think about 3-4 years back. As of last night, it wasn't compiling, but I made it to compile. Right, let me just quickly take us through, right? So what does it do, right? So this is the real world stuff. So I was learning some bit of machine learning, and so they had this Kaggle winners interviews. So the idea was that if I could just go through the interviews and see what techniques they've used, right, I could start practicing those techniques, right? Then these are the Kaggle winners. They're state of the art practitioners that have published their techniques, right? So the idea was good. So what I did was I essentially wrote a quick program to download all the interviews and put them in an Excel sheet and tag them. So this is vision, this is NLP, so on and so forth, right? Let me see if I have it still now. I probably don't. Screw it. I probably don't. It's on my personal one, right? But nonetheless, right? So the whole idea was that you download the web pages, the interviews. You extract the title, you extract the tags from the blogs, and then put them in an Excel sheet where you can filter by the tag. So let's say that I was trying to build a NLP application, right? So I could just select the, I could choose the Excel filter NLP, and then look at all the NLP interviews and see what they had to say about this specific problem, right? Right now, this is what a typical FP program looks like, right? So the main method is just a composition of goop, right? This looks like goop, but once you're comfortable with it, right, this will seem as easy as breathing, right? This is how you will think, right? But initially it might look like a bit of goop. But the main thing that is happening here, right? The code that I wrote is just the functions, this function, this, and this. These are the 4 functions I written, right? Now you can just see, right? And these are all very, so of course I defined the type. So what do I mean by an article? It's a title, the URI, so that I could click on it and go to that and read the details. The date when it was published, the older the article, lesser the value, and tags are essentially NLP vision or whatever, right? It's a list of tags. And then a CSV record is either an article or a error, right? So maybe the URI was not proper, or maybe there was the HTML was not properly formatted and things like that. So you can already see the type system starting to encode the awkward squad, right, which is errors in the system, right? So typically the way you go about it is first you define the types in the system, like this is a record type, this is a discriminated union, like what are the potential variants of types you might have to deal with, right? And often error types are first class citizen. Not often, always errors are the first class citizens, right? So you want to be able to handle both, right? So you are not keeping the awkward squad members to deal with them later on, right? And you're dealing with the happy path first. Everything is happy path. Awkward squad is the happy path, right? So the happy path is happy path. Dealing with the awkward squad is also the happy path, right? So this is what it indicates, right? Then what you do is you define the primitive functions. So if I want to get URL for a page, right, and now this has been heavily, this syntax means that compose this function with this function. So this function is nothing but the constructor, and this function takes a int and formats, you can guess percentage is the format thing. So get URL for a page. So given a page number, which is the pagination of the blog. So given a page number, get the URL of this. Then get the page for that, right? So this is asynchronous. So again, awkward squad, second member of awkward squad, right? Parallelism is the usual shit here. And again, error handling with error is the first class citizen here, right? So you either return an HTML or you return some very detailed error message, right? So you can see, right, these are all you're handling your errors first class, right? So the way to look at it is there is no happy path, sad path, right? They're all happy path, right? Handling errors is a happy path. And then finally, of course, you get down to the usual, right? This syntax is a funky syntax, but just think of it as you're taking the output of this and passing it to the next guy, right? This is just chaining of functions. People that are used to PowerShell, it's the same as this, right? The pipe operator. Right, and there are some diagnostics. So this is the second primitive atomic function, and the third primitive atomic functions I use something called an external library. Again, awkward squad number 3, which is external libraries. Right, so I use the XSL select stuff, and this one comes from a library called HTML agility pack. So it's like a very they've built it for the last I think 10 or so years, and that takes care of a lot of corner cases of HTML parsing. So HTML is like a very forgiving language. This does a good job in handling all of those vagaries of HTML. So once you've parsed that, once you've extracted, you go to the footer, extract the node, extract the, you get the idea, right? So you extract not only the tags out of here, but also the date and the URL and so on and so forth. And finally, you construct a record and return it outside. If there is an error, again, you return. Error is a first class citizen, right? So we've already seen 3 members of the awkward squad, right? And actually the 4th member is the input and output. So which we are already doing, right? This is external world input output. So what you typically do is define your type system, and errors are first class citizen of your type system. You define your very primitive functions. You unit test them. I haven't unit tested them here, right? And then these are your atomic functions. And finally, what you do is just compose them. That's it. These are all compositions. These are all library functions. The list.async, async.map, async.run synchronously. These are all provided by the library, right? These are all either community library or the core library, right? So this is just a copy. You don't even have to test these functions. So the main thing is once you compose this, right? Now, if for folks that are interested, I've given the URL of this. You can actually break down and play with the signature, right? For example, after first few lines, the resultant signature is this, right? So it's an async result. Result is something that indicates whether it's a success or a failure. It's a maybe type, right? So either it's a result of list of strings, which is a list of URLs, or errors, right? And similarly, after the second step, this is the signature. So as you see the signature evolve, right, you get an idea of what the code is doing. So technically what you've built is, right, when you have built your program, it's not like, oops, my code is executed. No, your code isn't executed till the runtime executes this main function, right? So till this time is just an expression. So your code is not executed at all. It's just an expression you're handing to the runtime, right? And then the runtime takes it over and executes it. So you've built your code separately, you've built the structure of your code separately and given it to a runtime. Runtime does the rest of the things, right? So that's the beauty of it. So you've converted very many impure, very input-output, very error-handling code into just pure transformations of code, transformations of types, right? So for example, the type int goes to URI with this function. Then the type URI goes to async result with this function, right? So on and so forth, right? You get the idea. Right, so this is essentially, so I'll get back to the, you guys feel free to ask me any questions you have. Maybe how do I share this? Right, so I'll stop my sharing. I'll get back to the slides, but if you have any questions, feel free to stop me, right? So
Will you get into what is a discriminated union?
Oh yeah, I did not, but I should show you that. So discriminated union is essentially a sum type. So it's a type that could be one of 2 possible types or 3 possible or 100 possible types, right? It's it could be an article or it could be an error, article error, right? I'll cover more of the discriminated unions down the line, right? And if you want to convert to a CSV line, you must handle both, right? So each line in the CSV can come from an article or can come from an error article, which means in the final Excel sheet, right? I should have shown it, right? You can either have a fully formed CSV line, or you will see a nice cute error saying that, hey, could not download this because of so and so reason, right? Did that answer your question, Andrew?
Yes, thank you. I was gonna after this explanation that what is in general. Thanks.
Okay, okay. So I'll cover more of this certainly. Right? So let me get back to the crap. Let's see. Right, so that's essentially a real world handling of awkward SWOT. Now, there are many other examples, and these are all some of the stuff that I initially wrote when I was first starting to learn out of my sabbatical after my first stint at Microsoft back in 2015. This test-driven development studio is something that runs your unit tests while you're writing your code, and this is a Visual Studio plugin. So I got it to the state where I could develop it using itself, if you know what I mean. Right, so it was self-dogfooding. So I got it to that state, so it was reasonably complete. That was the definition of done criteria, and I left it after that. It's available there. This is I got this to the state where it could actually boot up a 5150 ROM and self-test the CPU, right? And after that, I got into the PIC, and then I got bored and I left it. So it's somebody wants the region. This DNN is a nice DNN componentized library, fully unit tested, fully componentized. You can add your additional algorithms. You can add your own cost functions. You can add your own, a bunch of other stuff. So you can check it out, right? All of this is through pure functional programming, right? I think that there was just one mutable shortcut I took in the second one, just for performance purpose. But you can check out this real code, right? So this is real world stuff. Okay, let me get on to some of the basics theory. So hopefully now this section, right? I hope to break the if folks are going to be going into the mentality to ask how to write for loops in functional programming. Hopefully after this section, they won't be asking that question. Right? It's not even a wrong question in FP. So lambda calculus is formed by Turing's thesis advisor Church, right? Alonzo Church. Let's take a brief intro to that, right? So it's the simplest programming language ever, right? It's just three definitions. So x is a variable, so it's a lambda term. This is a function abstraction. It basically means that the function body is m, function parameter is x, and lambda is just indicates that it's a lambda. It looks cool. Let's leave it at that. Right, and m and n is function application, which means you're calling m with n. And now n could be any of these three lambda terms, or n could be, or both m and n could be any of these three lambda terms, right? So it is recursively applied. Right, so this is very simple. This is what the grammar for the language is. That's all it is, right? So you can actually, it's pretty easy to write a interpreter for this. This is the untyped lambda calculus, right? Now, three definitions, three terms, and then there are three refactorings or rearrangements, right? That makes it pretty funky, right? And with this, right, you will see why you don't allow mutations, and therefore you can never have for loops in functional programming. So first is rename parameter. So if you have a lambda x, 2x plus y, you just control R, the Visual Studio shortcut, and change x into z, and then x changes into z inside the function body as well. Fancy name is alpha conversion, but just call it rename parameter. Inline parameter, this technically is not a refactoring in Visual Studio, but you get the idea, right? It's inline variable, something like that. So if you have a lambda x with 2x plus y, and if you're calling it with 7, what you can do is in the body of the function, you can just, wherever x was there, you can replace with 7, right? It's so with beta reduction, if you essentially beta reduce the lambda term on the left with 7, 14 plus y is what you get, right? So you can see why it's called reduction and not conversion. Right, and finally the drop parameter, right? So so yeah, it's a fancy name, right? Now lambda x is sin x, right? So sin is already a lambda function is already a function with one parameter, right? So why just wrap it with a spurious function? So just lambda x to sin x is the same as sin, right? So both are taking in one parameter. That lambda x is a spurious part. So what you do is it sort of cancels the x on both sides and you're left with sin, right? So it just simplifies the notation. So that's an eta conversion. So again, it's a conversion, not a reduction. Right, so this is the brief introduction to lambda calculus. Now let's just take a quick look at what this can do, right? This is very powerful stuff. Right. So let's try and do something fun, right? And this is not fun. This is where Church's thesis is, right? Alonso Church's. Let's define true as this. This basically means it's a function with two parameters, and it returns the second parameter or first parameter, however you look at it. False, let's define false as this lambda term, which means it returns the second parameter. Okay, so this is a lambda function with two parameters, returns the second. And let's define not as this lambda term, right? Just blindly define it, right? Don't think, just stay with me. Now, can you see why not of true is false, not of false is true? So true is returning you the first parameter, which means in the not, you're passing in false and true. So it's returning you false. So not of true is false. Right? Okay, let me know if somebody can spot that, right? It's actually, you can work it out, but I think it's also, I mean, once you get the hang, it's like one of those magic pictures, right? Like you have to stare at it for a while and boom, you'll get the idea. Right? But the main thing is, right, you can build, this is called Church encoding, and you can essentially build Boolean algebra, not, or, and using not, or, and, true and false, you can build all of Boolean algebra. You can build numbers with plus, minus, star, divide, as far as I know, which means you can construct the entire algebra of numbers. You can define string operations and so on and so forth. Right, using just this notation, right? It's there online. It's a bit laborious to work it out, but once you work it out, right, you get the hang of it. Right, it's actually a lot of fun, right? But the main thing, right? Main thing, if you do this, right? I'm sorry, and of course, once you can do this, right, you can construct the entire programming language. So you can see that whatever can be computed by a computer, namely a human in 1930s, can be computed by this encoding, right? That's the main part. So you can build an entire programming language and a computation infrastructure, also known as a computer, using just this encoding, right? Now, this basically shows you like the theoretical basis of FP, sort of. It's very simplified. Like, for example, it doesn't have types, and we, at least as far as I know, we don't have a lambda calculus interpreter. I mean, all lambda calculus that we write still runs on a Turing machine, which is our one Neumann, the current PC, which is the one Neumann architecture, but that's basically a Turing machine, right? So it's, there are a lot of gotchas, but you get the idea, right? You get how you can pretty much do anything you want with this kind of encoding, right? Remember that there has not been a single mutation so far. So you've never replaced any variable. You've never modified any. There is no such thing as a variable here, right? There's never a word of variable, right? It's just replacing, renaming, and cancellations, right? Which means for you to do a loop, you don't have the basic construct of a loop, which is a mutation, right? So for you to have a loop, you need to have a increment, the counter, right? Loop counter. You can't have a loop counter simply because there's nothing for you to increment, nothing for you to mutate, and therefore you cannot have loops in, right? Right. So I think that should. Right. So let me know if you want to spend a bit more time on this, but I think this part is really funky. Like the first time I worked it out, right, it was really mind-boggling, right? It just showed that there is a new way to think about, reason about software, right? Now a quick detour, right? Functions in maths. Yeah, I'm running late. Now, what is a function in math, right? And how does it relate to functional programming, right? So what is this, right? So x is the parameter and m is the function body, right? It's the same function that you learned in math, right? Namely, there is a domain, there is a codomain, and function is a mapping, right? And both are sets. You take member of a set and map it to another member of another set, right? One to many not allowed. So you can't have one member of the domain map to multiple number. That's the not thing that is not allowed, right? Reverse is allowed. And there's no such thing as 2-parameter functions. Right, so it is functions in math necessarily imply right, pure functions in math. Note that it's just a mapping, there's no computation going on. So when you're writing f of x equals sin x, you're not really computing anything underneath, right? Computation is a way to find out the value, but technically it's just a number line mapping, right? So you have your f of the graph. In the graph you draw a line up and you see where it's meet the x-axis, and then manage the y-axis, and you see what the value is. So examples are for sin x, 0 maps to 0, pi by 6 maps to 0.5, pi by 3 maps to 1.0. Again, FP is best viewed this way. So when you're thinking about functions in FP, just assume them to be mapping, right? Don't worry about what they're computing, or if they're computing, right? Just don't think of as computation, just as mapping from one domain to another domain, right? And that is the most easiest way to think about, right? Otherwise you'll get into trouble in terms of reasoning. For example, a function into bool maps any item in the set int min to int max to the set false and true. That's all it is, right? Don't worry about the computation, right? Bool to string. String is again a set of all possible strings, all Unicode 65536 or multi-byte character string, whatever that number, that many number of strings permutated, God knows how many times, right? So from a set of 2 values to a set of that many infinite values, it's still a set mapping. That's the whole point, right? Yeah. So there was a deliberate mistake. It's pi by 2 or pi by, what is 90 degrees? Anyway, so I thought I'll just quickly introduce an error here. So the whole is the sine of 90 degrees, right? 90 degrees pi by 4, not pi by 3. Okay, so now that we are all looking forward to writing some code, right? So how do you go about it, right? So the way to look at it is, right, that all you need is a toolkit, and the toolkit is much simpler to learn than say some of the structured or the object oriented. Right? It's actually a lot simpler. I'll tell you why. Because it just has 6 patterns, right? The reason is, right, FP uses just those 6 patterns to handle entire awkward squad, right? And it's super consistent. So you just learn the 6 rules, right? Abstract them out into a library, and those were the async dot map dot list dot. Those were the functions that I had shown in the sample code. And they alone can handle the rest of the awkward squad, right? In more powerful languages like Haskell, it becomes much more simpler because they have the concept of types of types, right? It's like a second order type. Bad news though, it requires some getting used to. It's a bit mind bending, and no amount of thinking through that will give you that aha moment, right? There is no such thing as aha moment, right? Right. What can get you the thing is if you repeatedly write code, right? After a while, it becomes finger memory. That's the best way to get it, right? So don't try getting an aha moment, right? You can read it for the next 100 years and still not get what you would get if you wrote, say, 50 lines of code, right? So reading is not the way to go, right? So that's the main thing here. So just start typing code, right? And initially it will feel very alien. I mean, especially if you're used to O and structure, it will feel very alien, right? But after 100 lines of code, you will see, oh, okay, it's not that bad. After 500 lines of code, yeah, it's not too bad at all. After 1,000 lines of code, why would I write anything else? Would be the question in your mind, right? So even C# you'll start writing in this way, right? Good news again, getting used to this will require around 5,000 lines of code or 3 non-trivial pet projects, right? Ballpark, right? So if you can get past that number, right, you would have gotten the hang of it, right? And I can guarantee you, right, you will never get back to writing code any other way will feel alien to you, right? You'll be like, why am I doing this to myself? Now, it doesn't mean that FP is better or O is worse. It just means that some of these thinkings around these patterns, right, that need to start seeping it into your day-to-day programming, right? That's what makes you a better programmer. Right, and what are those toolkits? So there are the 4 aspects of functions. So I'll take us through what those aspects are, right? So when you say functions in FP, they are essentially, they have 4 aspects, 4 very critical aspects. 3 levels of types in the type system. So it's like, and for Haskell's, things like Haskell's, it becomes 4 levels of types. These are some of the funky sounding words, but they're rather stupid. Okay, they're very simple. Right? They just have fancy names because nobody bothered giving them any other names, right? Because I guess people have better work to do. But monads are mainly for dividing and conquering, affectionately known as MapReduce. Catamorphism for shaping and reshaping data. The Greek people here should recognize this. Right? Kata is destruction, morphism is transformation, destructive transformation. Right? For shaping and reshaping data, catamorphism, anamorphisms, this morphism, that morphism, there are 100 morphisms in this land. Monads, I don't know if this is a Greek term, for encapsulating all side effects with a consistent interface, right? This is the beauty of it. This is just beautiful. This is exquisite, right? This is exquisite, right? And actors, right? Actors for the concurrency parallelism, right? Because Moore's law has decided to give up on us, right? It thought we were too stupid. But nonetheless, we found actors, right? And actors come from 1980s, right? So it's not a recent invention, right? So let's quickly rush through as much as we can cover. In short, right, to get a hang of FP, pick up pet projects, write in pure FP. Don't take shortcuts. This piece is important, right? Your brain will fight. You need to fight back, right? Because brain will try to take shortcuts. But the main thing is, do not write mutable code, right? That alone will tell you everything you need to know about FP, right? Do not change a value once you have set it, right? That's the main rule. Once you do get an expert, again, it's not a religion. Once you do get some hang of it, once you do get some experience, right, then mutable just becomes another tool, right? But you shouldn't do mutable simply because you don't know any other way to do things, right? That's a bad reason to do mutable. But once you have options in your, like, not everything should look like a nail, right? Because you have only a hammer, right? So if you have multiple tools in your tool chest, then nail is a good thing to use when the need arises. Rinse and repeat till you cross 5,000 lines of code or 3 non-trivial pet projects. To master FP, keep writing code. Projects. Yeah, Antero has some awesome comments in the background. So you guys might want to take a look at that. Okay, so let's get on to, probably running late, and that's fine. We'll cover just part of it. Right, 4 aspects of FP. I think I'm going to stop using the term exquisite because I use it in every slide from here on. But it is exquisite. It is really exquisite, right? Now the main thing is, right, this gives you a way to reason about your code. Reason about your code is you can just logically read through and think through, right? And how do you build a bigger program? You take very small atomic programs and compose them, right? Exactly how you saw in that application, the sample application. You can check out in that TDD Studio. That is also very similar, right? And that's a non-trivial thing, right? Where you're actually asking Visual Studio to run all the unit tests in your projects while you're typing the code, right? So it's definitely a non-trivial project, right? And that is written in pure FP, no mutations. So check it out, right? And F#. So what are the 4 aspects of functions in functional programming, right? So aspect number 1, higher order functions are the thing, right? What is higher order functions? Basically means functions as arguments and return types, which means and C# has a lot of these days. Okay, I'll not. Have you done them already? Hell yes. In math, you've done it like this, right? So this is a higher order function, right? Where your sine square x is nothing but sine of x into sine of x. So those are 2 higher. This is a higher order function. In C#, this is a higher order function, right? So select is a higher order function. It takes in a value which is a function, right, and returns. You get the idea. F# very similar, very dumb, right? But the main thing here is, right, you are allowing functions to be arguments and return types of other functions. That's the meaning of higher order functions. The second aspect is curry. Yeah, this is named after Haskell curry, but I don't know if it has anything to do with his work. Maybe it has. And a related concept is partial application. Partial application, if you want, you can go into it later on, but currying is the main thing, right? Basically, in FP, there is no such thing as function taking multiple arguments. All functions take 1 argument at a time, right? So if you see a function with multiple arguments, the act of splitting them into 1 argument functions, sequential 1 argument function, is curry, right? So often library functions like .NET functions will have multiple arguments, right? And .NET is a imperative runtime. right? Do this first, do this, and do this. And to make it usable from a FP first language, like a functional first language, you will have to you have to do some currying. Yes, in math, we always do this, right? So this is essentially sine of x plus y. So you can think of it as a two-dimensional surface, right? The nice flowing thing. When you do currying, you're essentially taking a x plane with a given y and calculating all the values, right? You're seeing where that x plane intersects that entire surface, and then you do it for all the y planes. That's how you evaluate the function, right? In C#, yes, but it's pretty clunky and disgusting, right? Right? You have to take extra effort to make this happen, right? So these two are equivalent, right? But the type system is not very expressive. They don't have type inference, so it becomes a little bit gross, right? F# by definition is already curried, right? So this function that if you look at the IL, there is no two-parameter function. It is defined as a function that takes in an int, returns a function that takes in an int, returns an int, right? So it's already a curried thing. The third aspect of functional programming is pure and total. So this is the beauty. This is where a lot of the beauty comes from, right? Means it has no side effects, right? And it is supposed to have no side effects. But if you're running on a Turing machine, you can expect side effects. But if you ran on a lambda calculus interpreter or a lambda calculus runtime, right, then you would have truly no side effects, right? Actually, even then you would, because you're in real world. So that's pure, no side effects. And total means it for any given input, it will necessarily return an output. There is no such thing as a statement. It's all expressions. Given input, get an output, right? Which means now you can reason about your code. So when you see a line of code, you can actually start guessing, you can start inferring given the types, what it is likely to return, and whether the types from one part of the program actually matches the type from another part of the program. If it doesn't, you know that it won't even compile, let alone run. Yes, right. All math functions are by definition this way, right? C# can do, but other than trivial cases, it's really hard to implement. So acceptance, side effects, and stuff like that. Haskell takes it to the next level, but I think the fact that it takes it to the next level, it makes it very unfriendly for real world usage. F#, in my opinion, strikes a good balance, right? It tries, you can write as pure functional programming as you want in F#, yet depending on your needs, interface with the .NET class library. So this is why I think the F# usage is like significantly higher than Haskell or some other purer FP. Right, the language is tuned to make this very easy, right? The pure and totality, right? So you can write as pure FP code as you want, right? And pure FP is not for the religious purity, but it is just to make sure that you can reason about your code. What's the fourth aspect is the composition techniques. If you do the 1, 2, 3 aspects well, fourth aspect becomes very easy, right? So after that, how do you build your code? Non-trivial piece of code is like putting together a jigsaw puzzle. How do you fit this? So in normal jigsaw puzzle, right, you have the shapes that can fit with each other, or you get the idea, right? For functional programming, it's essentially the function signature, the output of your function signature. How do you morph that output so that it fits into the input of the next signature? That's essentially what the goal is in FP, right? Of course, other than writing those atomic functions, right? The main thing is if it compiles and your atomic functions are unit tested, your job is done, right? It's as simple as this, right? Right, if it compiles, that's the main thing, right? In Haskell, takes it one more level up. Haskell, if it compiles, it works, right? Right. Have you done them already? Yeah, you just saw the KW application. KW is the Kaggle winners archive or something like that. I don't remember what I named it for. This is how we do math. Math, super complex formula is a composition of individual formulas, right? C# it becomes really hard because C# has concepts of expressions, has concepts of statements. Void is not a type recognized by the type system. It's God knows what. I had another word for it, but I'm not going to use that. F#, of course, the code library, the language itself makes it easy to do that, right? Language, along with, yeah. So we will see in parts 2 and 3. Yeah, we have 10 minutes left. 3 levels of types in FP, right? So 3 levels of types is like, first we have the simple types, right? Int, string, booleans. Just treat them as sets. Don't overthink. Int is a set of int min to int max. All the numbers, I think there are about 4 billion numbers. So it's a set of 4 billion entries, right? Bool is a set of 2 entries. String is an infinite set, right? Or at least an uncountably large set. Is it an infinite set? I think it's an infinite set, subject to memory of the machine. Then algebraic data types, right? So simple types, the second level is algebraic data types, right? So check out this link here, okay? This is totally awesome, right? And I will go more in this in the second talk. So now you can start doing algebra with types, right? Which means your union types are nothing but sum types, which means the type, which is an int or bool, is nothing but a set which has all the elements of int and all the elements of bool. So all the 4 billion plus 2 entries. So that's what we're talking about here. This is not possible in C#, right? And give these guys some more time and they'll make it possible. Because somebody lacks job security in the team. Int and bool are tuple, right? Tuple is a product type, and you can also have records. Here it means that you have all the integers, all the 4 billion entries multiplied by 2. So now you have 8 billion entries, right? Finally, right, the beauty is this, right? The function type is also an algebraic type, it's an exponent type, right? So it's essentially all the elements of the bool type exponent to that many, the 4 billion. So it's 2 into 4 billion, right? And we can work that out if you guys want after the call, right? So you have sum types, product types, exponent types. This link has things like how do you differentiate? I think you can get to the Taylor series and things like that, right? I think the analogy is a bit stretched, but I think there's some beauty to that, right? You can check it out. But the main thing is, right, you have simple types. Using the simple types, you compose the types to come to complicated types using, so functions are just types. That's the beauty of this, right? Product types, sum types, and exponent types. Exponent types are nothing but functions. So you're all dealing with types, only types, and therefore higher order function means there's just another type. And finally, your flavors of types, right? So I think I will just stop with this slide. There was another section, but we'll resume it next time. Now flavors, right? This is a bit mind-bending, right? If T is a type, it's not the same as generics. Generics is a poor man's way to express flavor text, but don't confuse with generics. So if T is a type, M of T is another type that is basically T but with some flavor. Okay, some flavor. And what's an example? Task of int is an int that you will get back later, right? So it's a flavor of delayedness, right? Enumerable of int is one or more ints. So you can have 0 ints, you can have many ints. Option of int, you may have an int or you may not have an int. But these are all flavors of int, but it's basically an int. You get the idea, right? Which means that you can't add it as is. To add it, you have to do a bit more of gymnastics. But that's what the composition aspects come in, right? So you have essentially 3 levels, right? So you have simple types. Using simple types, you build an algebra, and using simple types in the algebraic types, you build flavors, right? So this is where you encapsulate side effects, you encapsulate a lot of the awkward squad behavior, right? You encapsulate them and convert it into another set of types. So awkward squad is nothing but types in the type system. So there is no such thing as a second grade or a happy path or a code path. Everything is happy path here. Now the mainly thing, right, the purpose of all this expressive type system is that the goal is to make illegal states not representable. So you can, if you know that my customer's name can never be more than 20 characters, you can actually write type. It's a bit hard in F#, but it's doable. So you can actually block creation of the type with more than 20 characters, which means that if an input from external world is coming saying that's like 50 characters, you can actually just review to start the program and give a straight away an error message or an error. You can take the error path, right? So which means that when you're running with the actual data, that's actually legal data that you're running with. So you never have to do another set of error checks if this is true, that is true, and things like that. The other thing is, right, it's very cheap to create new types, right? So unlike C# where you have to define one separate file and then one file can have only one type and those kind of crazy ass rules, you can freely create new types, right? You can just create a new type, this union, or you can simply, if you have a boolean type which has 2 members, and if you want another type which has say a type which is Partha and Vlad, right? These are the 2 developers, a type that has only 2 developers. You can just declare a type which is Partha and Vlad, right? Now that's identical to the boolean, but you would want to use the second one simply because it's more explicit. It names well, it reads well, but it's like true can map to Vlad and false can map to Partha, so they're identical as far as the functionality is concerned. At runtime they are identical, but it's more expressive that way. Okay, so I think I'll pause here because I have 7 minutes, but we will cover the 4 patterns next talk. I'll try and speed it up next time. So if you guys have questions, let me know. If not, I guess.
So how did you learn functional programming? Which language you used to learn these patterns?
F#, and I wrote these 3 apps. Actually, many other apps, but these were the 3 major ones.
So what's my take on this? I will say, no, there is some people have this approach to learning, like push the kid into the water and he will swim. Like that means in functional programming, just go and use a language that is tying your hands, like Haskell. Use it for some time, and when you come back, you'll want to do the same in OP language. And I want to say that for a lot of time, first when I learned programming, I started with this structured programming like Pascal and then C. And when I switched to OP for a lot of time, like years, I kept writing code as in structured programming. So I was not using actually OP, and I think this is the actual danger that you go. You learn the functional programming patterns, but if you go and use the same languages that we have today, like C# or Java, you're not able to put them in practice because you are regressing in the old ways. It's very easy to regress. It's actually the language is pushing you to regress. No, it's not pushing you to evolve. So it's really difficult. Even if I'm very passionate about Haskell, and I see how easy it is in C# to do it in the wrong way. I have to push myself every day to write good code in C#. It's really difficult.
I sort of mostly agree with you there. Mostly agree with the 2 points of disagreement, right? One is if you start writing in Haskell, right, you will not have access to the large library or large ecosystem that, for example, .NET has, or for example, Scala has access to the Java ecosystem, right? So that's the problem with Haskell. Haskell is a research language. They want to keep it pure simply because they want to push the bounds of functional programming. So it's not a real world, right? Now the second thing is, right, you do need language support to push you a little bit, but I think it's overrated, right? I think at the end of the day, right, if you figure out which parts of your code to keep pure and which parts of your code to wrap with some level of impurity, where to isolate the impurity, the main thing here is like, for example, Solid helps you isolate which parts of your system change and isolate them into only a corner, right? The most changing parts of your system you isolate into a corner using Solid. With the FP, what you're doing is you're isolating changes, you're isolating mutation to a corner of your system. So you're not having mutation willy-nilly all over the place. So that's what FP does to your code. So I think you do need language support, but I think even in C# you should be able to isolate mutations, or you should be able to isolate impurities.
Yes, you know what?
Non-laziness only to certain aspects of the code.
If I'm thinking to how you describe it, if you go to the function thing, to the 4 types of function, what I'm missing the most? Can you go back to the slide with the functions?
Sure.
The next one, I think, aspect number 2. No, aspect number 3, maybe.
Sure.
Yes, I think I missed this pure and total because I cannot easily have that sometimes in data algebraic data types. I cannot have the sometimes very easily, and I cannot get the very easily.
It's hard.
This matching. This is what I'm missing the most, and I'm regressing to using exceptions. So
yeah, it's hard. C#, it's hard to do this. It's really hard to do this.
It's definitely possible to have a written
Yeah.
code like this,
Yeah.
and also libraries that do this. But then kind of I was faced the challenges that I can't expose these types in my interface because others will just it will blow most of the people's minds. Like, sorry for saying that, and then also it will blow the people's minds who need to start maintaining this library after me, and so it's a really paradigmatic shift. So yeah, going crazy with functional concepts in C# world is a thin ice. I recommend going crazy once on a pet project, like Partha said, or something that it's safe to go crazy on, so you experience these things yourself. Writing like the either types or optional types, or even some smaller discriminated unions, maybe with three different members or so on. So you get a hang of it, and then you know what you're kind of missing or what to strive for. There are discussions in C# future that discuss this actively, whether we should and would have discriminated unions, but there's not really great information from them that it's anytime soon coming. But yeah, if I do my coding interviews for new hires, then I actually my coding exercise is about designing optional types, or like the result some type, like you said, this value or an error. The assignment is to implement the integer division without being able to use nulls or exceptions, and that kind of eventually drives you towards this. Not many do this, but it's a nice exercise to do on your own, even if you want to.
Yeah.
So actually, what is interesting, because I tried to use, we had a very good project in our team for this, and I tried to use as many as possible of these patterns in the project. And maybe it will be nice to present that real code that we wrote. It's like, it's a small project, but it turned out pretty well. And except these exceptions, we still use exceptions. Maybe it will be nice to present that that project at some point as a real case, a real world case in for functional programming in C#.
And some simple things like if you think about what is a factory pattern, it's kind of a function that returns unit of computation that cannot be a function. So a command pattern is really also about just modeling functions in OOP.
Yeah.
What one could say that.
Yeah.
A lot of such analogies exist, that if I go to the Gang of 4 book and take the patterns, then what is this pattern in functional programming? The joke answer is it's a function, but
Yeah.
but all these things kind of exist in OOP as well. We use them to manage complexity, and that's why functional program is built as well like this. But
Yeah, exactly. The functional program is just very limited. It's very highly unified, highly consistent. That's the beauty of it. All right, this was fun, I guess. See you guys next month.
Yeah, so thank you very much, Partha, for doing today's session. Wanted to remind everyone of the feedback form. If you want to write a session or you want to be a speaker, you can use that to register. We're always looking for new speakers. And yeah, see you next week and see you next month, Partha. Bye-bye, everyone.
Bye, guys.
bye-bye. Thank you.
Thank you. Goodbye.